Let me just quickly introduce myself. I'm Kanupriya and I work as a data science consultant in Bangalore. I have a bachelor's degree in maths and I have a master's degree in financial statistics from the London School of Economics. I'm also a member of the Royal Statistical Society and have been given a graduate statistician accreditation from them. So today I'll be talking about p-values and hypothesis testing. Why this topic? Well, it does seem something very basic. While, of course, this is something that many people will be familiar with or have at least come across, say, for example, in building regression models. With so many things out there to learn and to do, a lot of people have not had a chance to go in depth and truly understand each aspect of this. So I will try to explain this topic as how I would have liked to learn when I was initially first studying it. So what is hypothesis testing? Well, it is making a binary decision on a well-defined hypothesis. The null, which is denoted by H naught, usually states that there is no relationship between variables, and the alternative hypothesis, by extension, states that there, in fact, is some relationship that exists. We will start with the assumption that the null is the correct hypothesis until we obtain evidence that says otherwise. So to make the intuition more clear, I will start with an example. Suppose we are interested in estimating the mean salary of graduates from a certain university. Now we assume that the salary is normally distributed with mu that we do not know and with standard deviation 1. Now, of course, it will be very tedious and almost impossible to sample to record the salary of every graduate of that university and then truly know the actual mean salary. So what we'll do is, suppose we randomly select 25 people and we note their salary and we calculate a sample mean. Say it is 17 units. It may anything 17, say whatever, it's an arbitrary unit. So like suppose it's 17 unit represents $17,000 or whatever, right? So now we have 3 industry experts that give us their expert opinion as follows. Expert A claims that the mean salary is actually 16 units. Expert B claims that the salary is actually 15 units. And finally, expert C claims that the mean salary is 14 units. So now we have 3 people who've made this claim, but then how do we assess which claim is closer to what the true mean could be? So this is where a hypothesis test could come in. Now, so the first scenario where, let's say, expert A's claim is correct. So if this person's claim was actually correct, we will have the distribution of the salary as a normal distribution with mean 16 and standard deviation 1. Now let us look at where the estimate that we collected from those 25 people actually falls. So what we observe is 17, right? And looking at the graph, we can see it is only 1 standard deviation away from the mean. Now, given what we have observed as sample mean, this is only a little inconsistent with expert A's claim. Mathematically, the null hypothesis is that the mean is equal to 16 and the the alternate hypothesis is that the mean is not equal to 16. Now, under this given distribution, the probability of observing a sample mean of 17 or something more extreme than 17, such as 18, or perhaps if you go on the other side, 15, which is also one standard deviation away from the expert's claim, or say something even further extreme to that, say 14, the probability is about 0.3. Now, the next scenario is where expert B's claim is correct. Right now, if this person is correct, we will have a normal distribution with mean 15 and standard deviation 1. Now, again, let's look at where the estimate falls. Now we can see that it is 2 standard deviations away from the mean that expert B claims is correct. Given what we have observed as the sample mean, this is a little inconsistent with the claim. And mathematically, we can write this as null hypothesis with mean 15 and alternative with mean not equal to 15. Now, under the distribution, the probability of observing a sample mean of 17, something more extreme, such as 18, or going on the other side, something like 15 or 14, 14 or 13, something on those extremes, the probability of observing such values is 0.046, right? And moving on to expert T's claim, we will have a normal distribution with mean 14 and standard deviation 1. And looking at where our estimate falls, this time it's 3 standard deviations away from that mean. Now, given what we have observed, this is highly inconsistent because mathematically, we say that mean is mathematically the null is represented by mean equal to 14, and alternative that mean is not equal to 14. So now we're looking at observations on either side of 14. So now what we have observed, a sample mean of 17, the probability of observing such values, which are say 3 standard deviations away or more, is only 0.003. And like you can see from the chart, like the area that shows the probability is barely visible. It's just the thick line at the ends of the curve. Right. So what we really need is, how do we measure the hypothesis claimed and the discrepancy from that claim to what we have observed. So what we use is the probability. This measure is the probability of observing the sample mean or more extreme values, and we term this as p-value. Right. So now breaking down our example further, so we have 3 different null and alternative hypotheses combinations. So let's look at them one by one. Under the null hypothesis that the mean is 15 and the alternative hypothesis that mean is not equal to 15, the p-value, that is the probability of observing 17 or more extreme value, is 0.046. Moving on to mean equal to 14 and the alternative hypothesis of mean not equal to 15, we see that the p-value is only 0.003, and which means that the probability of observing 17 or more extreme value is 0.003. Neither of these seem consistent with what the experts have claimed. So we reject both hypotheses as the probabilities are extremely small, and a small probability event would not occur in a single experiment. Why? So going back to this graph, for example, so obviously it shows So if I have a mean around here, so obviously something like say 13 and 15, the area under here, which gives us the probability of the values being somewhere between here, is higher. So of course, if it's something more extreme, then the probabilities are less. So even if say the true mean was 14 and we took a few random samples, so we got 15 once, so we got 13, we got 14.5. So assuming that this distribution, these values are more likely because the probability of observing these values is higher. 17, however, the probability of observing that, and especially on just on a single trial, is very less, which is why we're comfortable with rejecting this claim that 14 is the actual mean of this salary of the mean salary. So let's formally define what the p-value means. So the p-value is the probability of the event that the test statistic, which in this case was the sample mean. So the probability of the event that the test statistic takes the observed value or more extreme values under our null hypothesis. Essentially, it is a measure of the discrepancy between hypothesis and the observed data. Right? So a small p-value, which would imply that our hypothesis is not supported by the data, as in, so the sample that what we have estimated from a sample is very inconsistent with what our claim is. And for a large p-value, that the hypothesis is not inconsistent with the data. Now, p-value can be seen as a risk measure of rejecting the hypothesis H0. So, for example, in the case where the p-value was 0.3, and it said that we're rejecting this null hypothesis, this is incorrect. So, comparing that to rejecting the null, which had only a probability of say 0.003, obviously it's a higher risk of rejecting the probability. Right. So how do we form a hypothesis test? So first, we always start with a null hypothesis and an alternative hypothesis. And how do we choose the null hypothesis? Well, that is something that is quite subjective, depending on what problem you're trying to solve, or based on what can easily be calculated. So uh, it's a mix of both. And then we define something called the significance level alpha. It is usually a number between 0 and 1, and which is selected again based on the problem. So usually, I mean, most generally, we have come across the significance level alpha is 0.05. And then we need a test statistic, and we compute the test statistic using the observations that we have sampled. So, for example, if you go back to where we're trying to estimate the mean salary, so the test statistic there was the sample mean that we observed. So once we have all of these things, we compute the p-value, that is the probability that the test statistic is equal or more extreme than what is observed. So once we have all of these things, the final decision is based on rejecting the H0 if the p-value is less than alpha, and if the p-value is greater than alpha, so then you cannot reject H naught. And sorry. So now let's I will switch over to R, and we'll have a look at an example of how hypothesis testing is used in linear regression. So what I will use a simple data set. So what the data set I'm using is the auto data, which is part of the ISLR library. This this data is it gives gas mileage, horsepower, and other information about some vehicles. And what I want to do is use MPG as the response variable and build a regression model. So let's start with loading the data. And these are the different variables. So MPG, that which, like I said, we'll be using as the response variable. And there's cylinders, displacement, horsepower, weight, acceleration, year, origin, name. Right. So not to overcomplicate things, I will just use 3 predictors. And so now the next question is, are those predictors related with the response variable? So before building the regression model, let's quickly look at our plots and form some sort of idea. Let's look at a few plots and form an idea about how these predictors are related with the response. So the very first predictor that I'll be using is cylinders. So it sort of looks like uh, as you increase the number of cylinders, the MPG goes down, but it's not a very strict linear relationship. And then there's few random points here. So while this may be maybe negatively related, I cannot say that there is a uh, strong relationship between these two variables. Then next, I'll look at acceleration and MPG. So while uh, you can see that there is some sort of linear relationship at the beginning, and on an average there might be a linear relationship, but then these are too spread out to actually say that this is a strong linear uh, positive linear relationship. And then finally, if I look at displacement, so this looks, of course, there's a negative relationship, and uh, this looks more strongly related compared to the other two predictors. So based on this, so the idea or hypothesis that I can form is that cylinders may have a negative relationship, but not as strong. Acceleration may have a positive relationship, but not as strong. Displacement has a negative relationship, may have a negative relationship, which seems stronger than the other two. Yes, of course. Right. So this is for loading the libraries. Then data is this function data is to extract this auto data, which is already in the library. And then names is to see what all the variables are in the data. And then I'm just creating some plots using ggplot. And I'm using the point values with the variables what I want to plot on the x and y axis, and then other things related like what color I want, labels, etc. So moving on to the actual model. Right, so I'm just using a linear model fit with MPG as the response variable. I think this might be better. Yeah. So I'm defining this model as a linear regression model with MPG as my response variable, and these are the three variables I want to include: cylinders, acceleration, and displacement. So I have cylinders, acceleration, and displacement, and the data that I'm using is auto. So I I personally feel that building linear regression models in R is quite straightforward compared to Python, but again, that's a personal preference. So this is my model, and then now let's view the model output. So usually what the output you have in a linear regression will give you an intercept, right? So because you have a formula beta naught, which is like the intercept line, then the variables that we use: cylinders, acceleration, and displacement. So like we hypothesis that we found that cylinders has a negative relationship. So you can see linear. Yes, so if I was doing a formal linear regression model building, yes, I would do all of the tests, possibly removing outliers, etc. But the purpose of this exercise is just to demonstrate the how we use the t statistic to form a hypothesis test. But yes, outlier removing is something that you usually do before you build a regression model. Right. So now that I have my coefficient estimates and I have my errors for those estimates, now we get something called the p-value, and the p-value here. Right. So generally, as many of you may know, you see the common practice. If p-value is less than 0.05, the variable is insignificant. Sorry, if the p-value is greater than 0.05, the variable is insignificant. And then you have something, these 3 points show how significant the variable is. So now we're saying the variable significant and insignificant is insignificant, but what does that actually mean? So for that, we use something called the t-test. So the hypothesis that we form is that the predictor X and Y have no relationship. And then the alternative hypothesis by extension is that some relationship between X and Y exists, which is mathematically we can represent it as beta naught, which is the coefficient for the predictor X is 0 versus the alternative hypothesis that the coefficient is not equal to 0. And this is how we calculate the t statistic. The coefficient beta divided by the standard error of beta. So essentially this measures the number of standard deviations that the predictor coefficient beta is away from 0. So in our regression output, this is our regression output, and so let's look at it variable by variable. So first we have cylinders, and so the t statistic, which is minus 1.273, it's calculated by dividing this number by this number. So this is the coefficient estimate, and this is the standard error this number here, standard error of beta. So that is our t statistic. We calculate it and we get a p-value of 0.204, which implies that we cannot reject a null hypothesis. A null hypothesis being that there is no relationship between predictor X and predictor Y. Sorry, predictor X and a response variable Y. Personally, for me, it really helps me to look at this visually. So let's look at it visually. So this is the plot for the t distribution. Our t statistics, which was minus 1.273, falls right over here and gives us a p-value of 0.204 approximately. So now you can see that this is not as far off from 0, and the probability of observing the t statistic, this value, given that just look at it again. Right. So I'll just answer this question. So R squared is a measure of an overall fit, not individual predictors. And R square is the R square value gives us how much variance is explained by a model. So just quickly go back to our model output. Right, so here you can see the R squared is 0.647, which usually is a decent R squared. That tells me, right, that, okay, this overall model explains some variation, but it doesn't give me any information about individual predictors. So that is where we look at the t statistic and the p-values. So once you have predictors that you're satisfied with, then you look at the R squared, and that gives you the information that overall your model may or may not be a good fit. So let's go in. Right, so you can see that the probability for observing RT statistic for cylinders, that was minus 1.273, is high. And when I say high, that's subjective. So if I took my significance level as 0.05, if I say that my significant level is 0.05, then of course, relative to that, this event, as it doesn't show those extreme probabilities. And there are examples, like in business sense, when you're building models in real life for an actual business problem, that there's some leeway, so a lot of times people are okay with even taking 0.2 as a threshold for a significance level. So if in a strict statistical sense, the preferable value is 0.005, but I have seen in practice that even a value like this would sometimes be okay. Right, so cylinder variable, if our significance level was set at 0.05, this definitely does not look this does not look like something that can comply with our test for significance. And looking at the hypothesis that there is no relationship between the predictor X and the response variable Y, we cannot reject that hypothesis. So seeing that this is what we observed as the t statistic, we cannot say that a relationship between X and Y actually exists. Then similarly for acceleration, this is the T statistic that we had. And this probability is even higher. So it is very close to 0. So it is likely that the coefficient for acceleration, it could very well be 0. And finally, looking at displacement. So the T statistic that we had was minus 6.9. And looking at the p-value, this is very small and it's barely visible. It's barely even visible in the chart. So there's a very small chance that the beta coefficient is equal to 0. So hence, we'll feel comfortable with rejecting the null, that there is no relationship between displacement and MPG. And hence we say that, right, that this variable is significant. So this is essentially how we say a variable is significant or a variable is not significant. Right, so that is all for my session. Please feel free to ask any questions if you have any, and I'll try my best to answer them.